Hey everyone, welcome to my talk, Always Watching, macOS Eavesdropping. I'm Justin Bowie and my handle is @SlideDog. So a quick introduction onto who I am before I start the presentation. Like I said, I go by the handle of @SlideDog. You can find me on GitHub, Twitter, and Medium. I'm currently a red teamer at SpecterOps. I work on red teams, pen tests, web app pen tests, and everything in between. I'm interested in all things security and skateboarding, as you can see from my little picture here. And I write non-pretty code that works. So a quick overview of my presentation. First, I'll be going over transparency, consent, and control, or TCC, on macOS. Next, I'll be going over a couple of the different languages that you could write post-exploitation capability in on macOS. After that, I'll be diving into 3 different TTPs: clipboard monitoring, keylogging, and screen capturing. I'll be diving into these at the API level to show exactly how these are done under the hood. Lastly, I'll wrap up with a demo of a new tool I'm dropping called SwiftSpy. All right, let's begin. So transparency, consent, and control, or TCC, on macOS was introduced in macOS on 10.14 during the Mojave update, and then further expanded in 10.15 during the Catalina update. TCC is essentially like privacy preferences or privacy controls on macOS. It stops apps from talking to each other and sandboxes them from accessing specific OS data or functionality. TCC will require user consent in the form of pop-ups when applications access certain data or certain system resources. The TCC daemon, or TCCD, is what handles these TCC requests. So it listens for these requests and will check that access in an underlying database to approve or deny an application's ability to do something. If you have worked on macOS before, you might be familiar with all these pop-ups. These are all due to TCC. So like Slack requesting access to your downloads folder, or Zoom requesting access to your downloads folder, or Zoom needing access to your microphone, things like that, all require approval by the user in the form of a pop-up. And so even if you deny it initially, you can always go back into security and privacy settings and enable it from there. So it's not a permanent setting. So here are a couple of the languages that you can write post-exploitation tooling in for macOS: Swift, Golang, Python 3, Objective-C, AppleScript, JavaScript for automation, or JXA, and C or C++. I went with Swift over some of the others just because I wanted more OS-specific support. I wanted like direct access to the macOS APIs, and also just found it a good opportunity to learn Swift, as I've seen other post-exploitation tooling written in Swift, such as like Cedric Owen's Swift Belt. So this is the MITRE ATT&CK knowledge base for macOS. You'll see that the TTPs, or techniques, tactics, and procedures, are broken up into categories such as initial access, execution, persistence, or privilege escalation. Normally when I want to learn more about a new operating system or a new tactic, or basically just a new language, I'll try to choose one of these TTPs and implement it. I've written Sharp Clipboard in the past, which is a C# clipboard monitor targeting the Windows operating system, and decided that would be cool to figure out how to make that work on macOS as well. So here's the MITRE ATT&CK entry for clipboard data, or like clipboard theft. It says that OSX provides a native command, pb paste, to grab the clipboard contents. So we could definitely grab the clipboard contents using these native binaries, but how is it working at the API level? Like, could we implement this ourselves? Before I dive into exactly how clipboard monitoring works, I wanted to dive into how to determine the current user's active application on macOS. I think this is extremely useful for just general context as an attacker to see what application the user is currently sending keystrokes to, or what application they're like clicking around on or whatnot. So I decided that to implement this first before implementing like a keylogger or clipboard monitor or anything. So the nice thing about determining the active application is that it doesn't require any special permissions. So there's going to be no TCC pop-up to the end user. To determine the active application, we use the notification center class. This class is used to receive NS notifications. NS notifications are essentially operating system messages on macOS. We register an observer that listens for the did activate application notification message. This message is sent when the user changes their primary application. And when we register this observer, we can essentially receive that NS notification when this event occurs. And when that event occurs, we'll just print out the current active application. So in the image on the right, you'll see me running SwiftSpy, and I'm just demoing the active application functionality. So I clicked on PowerPoint, then I went to Slack, then opened up the Bear app, then Google Chrome, Finder, and iTerm. So here's the code on determining the active application. In the first line, we're just creating that notification center object for us to interact with. Then we'll use the add observer class, and then we're going to listen specifically for this did activate application notification message. That message is the one that is going to tell us when the user changes their current active application. And then when that occurs, we're just going to print out the current running application. So next, we'll go into monitoring the clipboard. To monitor the clipboard, we can use the NS Pasteboard class. The NS Pasteboard class is used to interact with the clipboard. Similar to the active application implementation, this doesn't require any special permissions, so there won't be any TCC pop-up as well. Unlike the active application implementation, there's no message we can listen to for when the clipboard has changed. So we kind of have to resort to polling, which is a little less than ideal, but we can make it work. The NS Pasteboard class has a change count property. This property increases when the clipboard ownership changes. So essentially, we can poll for this value continuously, and then when this value changes, we can determine that the clipboard contents have changed and pull the clipboard contents. So on the right side of the image here, you see that from Google Chrome, I was able to just copy and paste the YouTube URL. And then from 1Password, I was able to capture the copy paste of this password. So one thing to note is that monitoring the clipboard as root is actually not possible. Root does not have access to the general pasteboard. If you look at the examples on the right image, in the first two examples, I'm able to obtain a handle to NS Pasteboard. So I get a handle here and a handle here. However, when I run sudo su tac-l, this creates an interactive logon as root. And then when I run the same commands, I actually cannot obtain a handle to NS Pasteboard. So if you run SwiftSpy as root, you actually will not be able to capture any clipboard data. So as an attacker, this is interesting because if we have original execution through root persistence, we won't have access to the pasteboard. However, if a user kicked us off as root, we likely still have access to the pasteboard. So this is how I implemented the Clipboard Monitor. In the first two lines here, pasteboard and change count, we're initializing that NS Pasteboard object. We're registering that change count value. And then after that, we're essentially running a while loop that will check this change count value every second. And if the change count value has changed, then we'll print out the current value that is on the clipboard, as well as update the change count value. And so we just loop continuously and continuously. And anytime that change count value is updated, we'll grab the updated clipboard contents as well. The next TTP I want to cover is keylogging. Keylogging is invaluable to attackers to just gather more information on what the user is doing, what they're typing, who they're talking to, and things of that nature. So keylogging on macOS uses the IO-HID Manager API. The IO-HID Manager API is used to interact with HID devices or human interface devices. One advantage of using the IO-HID Manager API versus CG Event Tap keyloggers is that the IO-HID Manager API can be run from low privilege, and unlike the CG Event Tap keyloggers. Unfortunately, keylogging on macOS is locked down with TCC and requires input monitoring permissions from TCC. These are the API calls that we need to perform keylogging on macOS. First, we'll use the IO HID Manager create API to create the HID Manager object that we're going to be interacting with in further API calls. Next, we'll use IO HID Manager set device matching. We're going to pass in a pattern to match specifically on keyboard devices. After we've matched in on just specifically keyboard devices, we'll use IO HID Manager register input value callback to receive a callback anytime an enumerated device sends input. So anytime a user presses some keys on their HID device, we're able to capture that input. Lastly, we'll use IO HID Manager open and IO HID Manager schedule with run loop to begin listening for callbacks. Here's a more graphical view of the API calls necessary for keylogging. So first, we'll use IO HID Manager create to create that HID Manager object. With that HID Manager object, we can pass it to IO HID Manager set device matching. Here, we're going to match specifically on keyboard devices because that's where we're interested in. If we pass in that HID Manager object to IO HID Manager copy devices, we can enumerate all of the keyboard devices currently attached to the computer. Going down here, we can use IO HID Manager register input value callback. So after we've applied that device matching filter, we can add a callback function to be performed when any input is received from an enumerated device. Next, we'll use IO HID Manager open to just open any currently enumerated devices. And lastly, we'll use IO HID Manager schedule with run loop to kick off a run loop that uses that device matching filter on keyboards that we've specified, as well as with the callback applied. So here's what the callback function looks like. In this first image, you see that IO HID Manager register input value callback. The second parameter into this is the callback function that we want to call anytime an enumerated device sends input. And so when an enumerated device sends input, this function is triggered, and then we can do post-processing on the event. So we can figure out exactly what the user pressed and things of that nature. So here's kind of what that looks like. With IO HID value callback, the callback function has this IO HID value ref value variable right here. That can be passed to IO HID value get integer value. And then the output of that is going to be a 1 when a key is pressed or a 0 when a key is released. Alternatively, we can pass in that IO HID value to IO HID value get element. This will return an IO HID element, which is usable with IO HID element get usage. IO HID element get usage will return an integer between 4 and 231 that specifies the key that was pressed. So now we know when a key was pressed or released and the value of the key. So we have everything we need to create our keylogger. So here's an example of keylogging on macOS. You'll see that I created the HID manager. I enumerated the devices. I didn't print anything for essentially setting up the device matching filter or setting the callback function. But if you look here, you'll see that I opened up Google Chrome, I browsed to google.com, I searched doggos, and then I opened up Slack, and then I typed my fake AD password into Slack. The last TTP I want to cover is screen capturing. Screen capturing can be done on macOS using the screen capture binary. But again, I want to figure out what this is doing under the hood and figure out if I can just implement it myself using macOS APIs. So screen capturing on macOS uses the Core Graphics API. The Core Graphics API actually requires the screen recording permission from TCC. So if we don't have it, the user will be prompted. Screen capturing on macOS is fairly simple. First, you use the CG get active display list API call. You pass in a null to the active displays parameter, and this will actually return the number of active displays that the user has. We call CG get active display list again, passing in that number of active displays, and we get a list of active displays that we can interact with. Next, we'll loop through this list of active displays and grab an image with CG display create image. And then we'll write that image to disk. So this is what that looks like. So first there's that CG get active display list. We're going to pass a null to this second parameter, which will actually fill this third parameter with a number of active displays. Once we have the number of active displays, we'll pass it back into CG get active display list to obtain a list of all of the active displays. Next, we'll use CG display create image to take a picture of that display and then write that image to disk. And then we'll repeat this for all the active displays. So I want to introduce SwiftSpy, which incorporates all of these different techniques that I've talked about. SwiftSpy is a macOS keylogger, Clipboard Monitor, and screen capture tool written in Swift. The code can be found on my GitHub at github.com/slydog/SwiftSpy. And I've showed the help menu in the image below. So you can see that SwiftSpy has keylog functionality, clipboard functionality. I've combined the keylog and clipboard module with the all keys flag. So this will run both of those modules to capture all the user's keystrokes. It has a screenshot module, and you can specify the folder that you want to save screenshots to. Additionally, you can specify a number, and this will basically run the screenshot module on a loop and continuously take photos of the user's current active display. So we're going to get into a quick demo here. Today, I'll be demoing to you SwiftSpy. If you run SwiftSpy without any command line arguments, or if you pass in the tac-h or tac-help flag, the help menu will be printed. Some of the modules that SwiftSpy has are the keylog module, which will record all keystrokes using those IO HID manager APIs, the clipboard module, which will record any copy-paste events. You can combine the keylog and clipboard module with the all keys flag, and all keys will basically simultaneously run both of those modules to capture all keystrokes. Lastly, there's the screenshot module. Screenshot, you can pass in the folder, and that's the folder that the screenshot module will save all of the screenshots of the user's active displays to. Additionally, you can pass in a number to the screenshots module, and the screenshot module will run on a timed loop and continuously take a picture of the user's active displays. All right, let's dive into some of the functionality. So first, I'll demonstrate the keylog functionality. And so if you do SwiftSpy and you pass in the keylog flag, we'll see here that we could not open the HID manager. And this is because we haven't enabled the input monitoring permission within TCC. So if we do that now, we can get past that. So if we enable that for iTerm here, I will have to restart iTerm. So if we restart iTerm here, and we again do SwiftSpy-keylog, we'll see that this time the HID manager was successfully opened. And so now I'll go here, I'll go to google.com, and then I'll Google kickflips. And so you'll see right here that we were able to record me browsing to google.com as well as kickflips. So that kind of wraps up the keylog module. The next module I'd like to show is the clipboard module. So if we do SwiftSpy and we pass in the clipboard flag, this will monitor continuously for any new items on the clipboard. So if we click over to 1Pass here, you'll see that SwiftSpy notified us of the 1Password application being the main application. And if we go down to the password here and we hit copy, SwiftSpy is able to detect this copy event and shows us the clipboard data here. The last module I'd like to show is the screenshot module. So if we do SwiftSpy, tag screenshot, and let's say we want to save them to temp. Since we didn't enable screen recording within TCC, we're now getting a prompt. So it hasn't been enabled yet. However, if we do an ls on temp, or start.jpg, we'll see that there are 3 images. If we do open, so these are the 3 images that the screenshot module was able to capture. This is because when TCC has not enabled this permission, you can still take a picture of the users' active displays, but you won't capture any useful information like the windows or applications that they currently have open. So let's try again with enabling that privilege in TCC. So if we enable it here, it's going to make us restart iTerm again. We're going to remove those old JPEGs, and we're going to do SwiftSpy. So now we're going to check for the existence of our new images. Then we're going to open them. So you can see here, now that once we've enabled the permission within TCC, we're able to capture all of the different windows that the user currently has open. So that concludes my demo. I want to give a huge shout out to Cody Thomas, or at It's a Feature on Twitter, and Chris Ross at XOrrier on Twitter for answering all of my noob macOS questions. Here are some of my references, and yeah, I'll open the floor to any questions.